Geometry, Chapter 7, Section 2. So I had to use the mouse to do that. Look at that, my finger's working again. Okay, similar polygons. We have studied congruent polygons, particularly congruent triangles. And we learned a whole bunch of ways to prove triangles congruent. Do you remember some of those ways to prove triangles congruent? Side, angle, side. We can do all the corresponding parts. That's the definition. Shortcut, side, angle, side. Side, side, side. Side, angle, side. I think that was my first one. Angle, side, angle. Well, we're remembering a few of them. What does it mean to be congruent? Equal. In what way? All measures. So if we're talking about polygons, what are the measures we have as polygons? What can we measure? What measures do we have in polygons? We have angles, and what else? And we have sides. We have angles and sides. If they're congruent, all angles and all sides, corresponding angles and sides, are congruent to each other. If they are similar, we need to learn what that means. Right over here are a picture of two similar, what do we call six-sided figures? Hexagons. Two similar hexagons. The corresponding angles are congruent. Those are exactly the same size angles. Are the sides exactly the same size? No, they are not. So let me give you some hypothetical lengths. Let's say this one is 2, and let's say that one is 4. Let's make this one 3. I know these really are equilateral, but all the same size, regular, but we're just going to imagine for a minute. And this one is 6. Do you notice any relationship that's beginning to develop between those sides? They're multiples. They're multiplied by 2. Or if you think of what we learned in the first section, they are equivalent ratios. If I go 2 to 4, is that the same thing as 3 to 6? Yeah, they are. They are proportion. When two ratios equal each other, that is a proportion. They are proportional. 2 to 4, and those are my corresponding ones, equals 3 to 6. There are also some corresponding ones. That is a proportion. So what we have for a definition of similar polygons is they are two polygons whose corresponding angles are congruent and corresponding sides are proportional. That makes them similar. In everyday language, we would say they are the same shape, but they are different size. That's what similar essentially is. Same shape, but different size. Now, technically, congruent polygons are also similar ones because they have ratios that are exactly the same. If one side is 2, the other side is 2. One side is 3, the other side is 3. Well, 2 to 2 is the same thing as 3 to 3. It's a scale factor, we're going to run across that, of 1. We call the proportion the scale factor. We might as well bring that up since I just said it. The scale factor is always the reduced ratio of any two corresponding sides. So if I use those two sides and I reduce it, and it doesn't matter which two I reduce, I get 1 to 2, or let me write it this way, 1 to 2. That would be called the scale factor of the smaller one to the larger one. What do you think the scale factor of the larger one to the smaller one would be? Yeah, instead of 1 to 2, it would be 2 to 1. So it's important the order we go. Two polygons are similar if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. So there's our definition. And they have down here given us an example where they have shown, hey, these are all the corresponding angles. They're congruent to each other. And here are all the corresponding sides. And they all happen to be ratio of 3 to 1. That's going from left to right. The symbol, when we did congruent, we did an equal sign, and then that squiggly line above it, almost got that complete squiggly line. The equal sign comes from equal. They're congruent. If we drop the equal part to it, that symbol is for similar. One polygon is similar to another polygon. I promised yesterday that we would talk about that prime. Here's what we sometimes see written. If I take this first polygon, ABCD, and I match it up with its corresponding parts, instead of using these letters, I could call it A prime, B prime, C prime, and D prime. It kind of indicates which ones pair up or match with each other. So if you ever see that notation, oh, I'm familiar with that. That just means another letter. A and A prime are two different letters, but they often have some sort of relationship with each other. So what do we do with this? Well, one of the things we do with it, it says if triangle FGH is similar to triangle JKL, they want us to list all pairs of congruent angles, and then they want us to write a proportion that relates all the corresponding sides. And they want us to use the similarity statement. Well, here's the similarity statement. We already learned when we talked about congruence that we need to match up the vertices that are corresponding. So F and J match up. F and J match up. Those are the corresponding ones. It's been rotated, so don't be confused by that, but if I'm going to match them together, those are the two that are the same size. G and K match up. So when they say similarity statement, it's just like writing a congruent statement. Make sure your letters are in the right order. And then if they are in the right order, then I know automatically F and J, those two angles, are the congruent ones. And G and K are the congruent ones. And H and L are the congruent ones. So there's all the corresponding angles. And then I can go back and I just start with the sides. FG must go with JK. So FG to JK is the same thing as, I'm going to do it underneath, GH and KL. GH and KL. Then I can keep on going, and the first and the last. F and H, the first and the last. J and L, the first and the last. They did HF and LJ, doesn't matter which order we do, and so we extend it to a complete proportional statement. So let's try it out right down here. They say in the diagram, polygon in PQR is similar to polygon UBST. List all pairs of congruent angles. Write a proportion that represents the corresponding sides. So you look at the picture, and I want to know what angle is angle N congruent with. U. Angle N is going to match up with angle U. You have to, in your mind, kind of rotate that around to try to find the matching sized angle. And let's go to angle P. Angle P, what is that one congruent with? V. Angle P is congruent with angle V. Angle V. And angle Q is congruent with angle S. And by this point, hopefully you don't get anything wrong, angle R is congruent with angle T. Excellent job. So there is the statement of all pairs of congruent angles, and then they want the proportional statement with all the sides. So I'm going to start with NP. NP corresponds to UV, which is going to be proportional to, I'm going to move on to PQ. PQ goes with VS. Then I'm going to move on to QR. QR, proportional with ST. And we have one more. We have RN. For all you medical types, RN corresponds with TU. There's a UE. Which way were we going? UV should be TU if I keep my orders all right. TU. There we go. There are all the proportional sides. Scale factor. I told you what the scale factor was. In the diagram, they say that triangle ABC is similar to triangle XYZ, which means A matches up with X, etc. The scale factor is 6:3. So if we look at side 6, which is AB are the first two, so XY are the first two. XY right over there, sure enough, it goes with the 3. And we reduce 6 over 3, we get 2. Now the deal is, if I want to write that as a scale factor, 2 to 1, or you could write it as a fraction, 2 over 1. But a scale factor, really would like to see it with the two numbers there, 2 to 1, even though if you simplified it, that's just the number 2. Now that's the scale factor when you go in the order from ABC to XYZ. If you change the order XYZ to ABC, you need to turn it upside down, and the scale factor becomes 1 to 2. So just remember that the order is important to us. So using the scale factor, determine whether the triangles shown are similar, and if so, write the similarity statement and explain why we knew they really were similar to each other. Two things make two polygons similar. What's the first thing we need? And there's really no order. What's one thing we need? Not similar angles, congruent corresponding angles, or equal in measure corresponding angles. And the second thing we need is something about the size, something about their ratio. They must be proportional, which means they have the same scale factor, or their ratio reduces to the same thing. So let's start with the angles check. Do I have all three corresponding angles congruent? I notice N is congruent to R and Q is congruent to S. How about P and T? Do I know they are congruent? Yes. Can you tell me why? Somewhere in your memory. Well, that's the reason, because other two angles are congruent. We have a third angle theorem that says if two angles in one triangle are congruent to two angles in the other triangle, then the third angles must be congruent. Check. Now we need to check the sides. So if I am going to check the sides, I've got to work on some proportions. Let's take that 12.5. That 12.5 corresponds with what?
10.
The 10. Now that doesn't really tell me anything, but I'm going to check. I also have an 11.5, and what does that correspond with? The 9.2. How do you know it goes with the 9.2 instead of with the 12? You can kind of think of how it's rotated, if you will. Some of you can visualize fairly easily the rotation relationship. Some of you don't see it quite so easily, so let me show another way that we can do it. Let's start with that 12.5. That 12.5 is between the 1 and 2 marks they have done. So I go between the 1 and 2 marks, and I know it has to correspond with the 10. Then the next thing, if I pick the 11.5, now I want to look in this original. That 11.5, is it the longest length, the shortest length, or the one in the middle? It is the shortest one. So if they are really going to be proportional, it is going to have to match up with the shortest one and the other. There's another way of telling what matches with what. And using that same idea, again, if you can see the rotation and how it matches, you can use that. But here's the other way. If I go on now to my 15, I notice, hey, that's my longest side, so it's going to have to match with the longest side if they are going to be proportional to each other. So this is what we want to check. I don't know whether this is true or not. So this is what we want to check. How can we check it? Can you give me any ideas? There's a couple of ways I might do it. Any ideas how I might check to see if this is true? How do I know if those fractions equal each other? Divide. That's one way I can do it. Let's do that. Take 12.5 and divide it by 10. Tell me what you get. 1.25. Take 11.5 and divide by 9.2. What do you get?
1.25.
1.25. So far, so good. Take 15 and divide by 12.
1.25.
1.25. Check. Now there's another way. Can you think of another way? That's one way. That works. They all are the same ratio. How did we solve something like this? We took the cross products, didn't we? And what do we know about the cross products? They must be equal to each other. That is another way I can check. Why don't you come back here, and I want you to multiply 12.5 times 9.2. What do you get? 115? Multiply 10. You can do this in your head. 10 times 11.5. What do you get? 115. I know those are equal to each other. Now I'm going to take the next pair, not the same cross product. take 11.5 times 12. It's not going to be 115. 138. What's 9.2 times 15? 138. There's another check that you can do. Take the cross products. See if the cross products are equal. So there's a couple of ways that you can check. They wanted us to answer, are they similar? We decided absolutely. And why did we decide that? Because the angles were congruent and the sides, what about the sides? Were proportional. So I need to know both of those, and if I know both of those, I know we have two similar polygons, in this case, two similar triangles. Find the value of each variable if triangle JLN is similar. So they want us to figure out what x is. So let's find x over here. Well, if these things are similar, what do I know about 6x minus 3? Now, it doesn't necessarily equal 3, but it must be proportional to 3, or the same ratio as... Now, I need something else so that I can set up my proportion. Now, I don't want to introduce my y because then I'll have two unknowns. Anything else that matches up that I know?
4 and 2.
The 4 and 2. The 4 and the 2. And those are things that I know. Now I'm going to reduce this for a moment. 4 over 2 really reduces to, and I'm going to say 2 to 1. That's known as a scale factor. 6x minus 3 over 3 must equal 2 to 1. So if I take the cross products, now when I multiply by 1, nothing changes. Equals 3 times 2, so I know that's going to be 6 there. So 6x minus 3 equals 6. I'm going to add my 3, so it equals 9. I'm going to divide by 6, and then you're going to reduce.
1.5.
Okay, you can call it 1.5. What fraction is it? 3 over 2. It is true that it is also 1.5. There's x. We figured out what x was. Now let me do the second part, how I usually approach them. The very first thing I look for when I have two similar figures is what is the scale factor? Now we did that. We figured out the scale factor was 2 to 1, going from left to right. So I start with my scale factor and say any other measure of length going from left to right must be in this ratio of 2 to 1. So now 3y minus 2, what does it go with? It goes with the 5. So I know 2 to 1 is the same thing as my 3 minus 2 over 5. So 1 times 3y minus 2 is 3y minus 2. 2 times 5 is 10. I'm going to add my 2 and get 12. You're going to divide by 3 and get 4. We know what y is. So this second column is how I always do mine. I figure out what the scale factor is first, and then I set that scale factor equal to whatever other ratio they have given me. Perimeters of similar polygons. If two polygons are similar, then their perimeters are proportional to the scale factor between them. So not only are the sides proportional to each other, but if you added up all the sides, those perimeters are the same proportion. So they are saying this statement, that's the ratio of the perimeters, is going to be exactly the same as every single one of the other ratios, or the scale factor. So we are going to use that fact to help us here. So they tell us we have two similar polygons. It says find the scale factor, and they want us to go MNPQ, this one to this one, that's the order they said, and figure out what the perimeter happens to be. So if I'm going to find the scale factor, I need two corresponding sides that I know the numbers. 8 and 4? 8 and 4. So let's see if we can kind of rotate around in our minds. That looks like those are the two that are going to match up to each other, doesn't it? So if I'm working on the scale factor, 8 to 4 reduces to what? 2 to 1. There's my scale factor. Then I'm going to find the perimeter. Well, I'm going to use that scale factor. 2 to 1 must equal the perimeter of the large one over the perimeter of the small one. And the perimeter of the small one is what I don't know. I do know the perimeter of the large one, or at least I can get it. How? Add them up. So, Mr. Fisher, what do you get when you add them all up? Or anybody? 34? Do you agree? And just saying yes without trying it out does not give you or me any confidence. 34? So I know the perimeter of this big one is 34, and the perimeter of the small one is, well, I don't know, but I can figure it out here. 1 times 34 is called 34, 2 times p, and divide by 2, what's the perimeter of the small one? 17. They wanted to know the perimeter of each. One is 34, the other one is 17, and we use the scale factor in order to get that. I think I am done talking, and now you can work on a worksheet.